Okay, for example 3, we're going to find the derivative of f of x equals x cubed plus 2x using the limit definition of derivative. If you looked at example 3 Wednesday and it made sense to you and you were able to follow through what they did, you can zoom ahead in the video. If not, I thought this was worth us doing. So, oops, I forgot my limit. So that's equal to the limit as delta x approaches 0. We're going to put all of this right here and right here in place of those x's. So that's what we get when we do f of x plus delta x. And then it's minus the entire f of x function all over delta x. I think this is a great problem because it reviews Pascal's triangle for you. Remember, this is the 0th row's coefficient, first row, second row, third row. These are the coefficients for the third row. Those are the coefficients for a plus b cubed. So, we're going to write out our coefficients. Hope I have enough room. This first a starts at 3 and goes down. And then x to the 0, right? So I don't want to write those parts. And then b starts at 0, which I don't want to write, and grows. So let me take that x to the 0 off. So delta x squared, delta x cubed, and we will join those with pluses. Then we can distribute here, and then we can distribute this negative. Lots of things should divide out for us, or subtract out for us. The x cubes do, the 2x does, and do we have any like terms? I don't think so. So it's equal to the limit as delta x approaches 0 of 3x squared delta x plus 3x parenthesis delta x squared plus parenthesis delta x to the third plus 2 delta x all over delta x. So every single term that I wrote down has a delta x in it, so I can divide out a delta x from every single term. So this delta x is gone. I'm going to mark out that exponent, so I've just left one of those delta x's. This is a 3. I'm dividing one of them out, so I'm going to mark it out and put a 2. That one got divided out, and that one got divided out. So now what's equal to the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared in parentheses plus 2. Once I'm able to divide something out, I should be able to do direct substitution, so I can put a 0 here and a 0 here. So we're equal to 3x squared plus 3x times 0 is gone. 0 squared is gone, and we're left with just plus 2. And that is your derivative. Okay, example 5, we're going to find the derivative with respect to t for the function y equals 2 over t. Remember this WRT from symmetry and even and odd things? We wrote this down. That meant with respect to. Okay, so we want to find the derivative by the limit process. If we're dealing with t, then all of my x's are now t's, so it's delta t of f of t plus delta t minus f of t all over delta t. Last year, Coleman Burrow said, I just change every one of those t's to x's because t's look too much like plus signs. I couldn't agree more. So maybe you just change them all to x's. Okay, equals the limit as delta t approaches 0. Now we're going to do this first part. We're going to go to our function, which y is f of t in this form, and we're going to put everything right there in that t. So it's 2 over t plus delta t minus, now we're going to just write down the f of t all over delta t this is a fraction. We're going to do a butterfly to get common denominators of this subtracting fractions. So it's 2 times t for the first wing minus 2 times t plus delta t for the second wing. And then the bottom of the butterfly, these denominators get multiplied together. And don't forget it was all over delta t. You're going to do a little distributing in the numerator. I recommend you not distribute the denominator. Some things are going to subtract out. And let's take care of this division with delta t. Let's make it a fraction. And let's flip it up here and multiply by its reciprocal. Almost done. So that's equal to the limit as delta t approaches 0 of, let's see, we can let these delta t's divide out. Negative 2 over t, parenthesis t plus delta t. As soon as something divided out, we're probably ready to direct substitute. So that's negative 2 over t times parenthesis t, negative 2 over t squared. Okay, so I've written, if a function is differentiable, it is continuous. That's guaranteed to be true. If I can take its derivative, then it is continuous. However, the converse is not true. In geometry, you might remember where we did CCIC, and we had the conditional, converse, inverse, and contrapositive. The converse was the logical statement that switched the hypothesis and the conclusion. So it is not true. You cannot say if it is continuous, then it's differentiable. So that's not true. Not always. That is not always true. Let me give you some cases where it's not. One case where it's not true is if you have a graph with a sharp turn. What type of graph has a sharp turn? Absolute value graphs have sharp turns. And since we've been talking about how derivatives, one application of a derivative was slope, let's just look at the slope of this line. That's a negative slope. I don't know what value it is, but it's negative. And then look at the slope of that line. That's positive. So these two values aren't the same. I have a sharp turn right here at this point right here. I decrease and then it changes abruptly and it's increasing at a sharp angle. That is not differentiable. A graph with a tangent, a vertical tangent line. Let me just do that on the next page. That is not differentiable. What would that look like? It looked like this. And if you wanted the derivative right here at that point, it's continuous, but it's got a vertical tangent line right there, so it's not differentiable. So theorem 2.1, if f is differentiable, at x equals c, then f is continuous. At f x equals c. So if it's differentiable, then it's continuous.